Okay, so welcome to the second lecture on selected topics in graph theory. Today's lecture will be rather lightweight in the sense that we are going to introduce graph minors and treewidth and speak some basic properties about it, but not, but don't go into very complicated proofs. The next lecture will be mostly a large proof that will be, we will prepare today the ground for the proof next lecture. Okay, and I'm reusing some slides we are using on Algorithmika course with Łukasz Kowalik here, and also there's actually I think one slide by Michał from some other lecture up there. So some of you that attended Algorithmika may recognize some slides, but the shift or like the point of view will be significantly different on the Algorithmika course. So please listen, I'm just reusing some of the pictures and slides up there, but speaking a bit from different angle. Okay, so let's go further. So we'll be doing graph minors. And so let's first define what does mean to be a minor. So being a minor is a relation between graphs. It's like a partial order between, it's really partial order in the set of graphs. So we may say that a graph H is a minor of a graph G. I mean, sometimes you can in literature find like inequality with M somewhere here or somewhere at the top. We don't have any fixed notation here really to be like being a minor. And one of the ways of defining it is to have a minor model up there. So let's go over the details of the definition. What does it really mean? That means that, okay, I have got a graph G. So this is the large graph, like a host graph. And inside there, we find disjoint sets and say that the graph H is, I don't know, a four cycle. Graph H is a four cycle, and the minor model of graph H inside the G will be four disjoint connected sets. So they're connected. I mean, there's some things are connected inside, and there are additionally edges between the. Sorry, there are additionally edges between the. I mean, let's use different color for that. There are additionally edges between these branch sets. They're usually called branch sets, that make this four cycle. Yeah. So in a sense, you can find this four cycle inside this graph G, but every vertex can be replaced with a connected set, and this set needs to be disjoint. Okay, so this is like a minor model, and now we say that H is a minor of G, because I mean you can find this subgraph looking like a four cycle inside graph G. Okay, maybe four cycle is not a good, it's not the best example, but if we were looking, for example, at this graph, then we would additionally require that there's additionally like an edge somewhere from this set to this set like that. So we have got something that looks like this graph H on the right, but every vertex can be a connected set, and this connected set needs to be disjoint. Okay, so this is like a minor model definitions. These blobs are usually called branch sets. These sets are usually called branch sets, this IU. And yeah, this is a minor model. But if you think about it, you can also think about it in terms of operations. So if you look about at this graph G, you can discard everything else from the graph. So you can take graph G, discard everything outside here, and contract the edges inside these branch sets and obtain graph H. So you can alternatively say that a graph is a minor of another graph if you can turn the larger graph into the smaller graph by deleting stuff. You can delete edges and vertices, and you can contract edges. Okay, and contracting edges means that okay, there's an edge that you want to contract, and maybe there are some edges going out, and maybe there's some common neighbor, and that means that you make from this x and y, you make one new vertex, call it w, and you have the same neighbors. So you have got this edge is going out there, this edge is going out there, and this edge becomes an edge to this guy. You don't keep double edges in contraction. We are just looking at simple graphs. We don't have multiple edges in most of the things we are going to speak about. There are no multiple edges. Multiple edges don't make sense here. Okay, so this is edge contraction. And yeah, so you can think either in terms of minor models, this is sometimes useful way of thinking, or sometimes in terms of the sequence of operations, deleting stuff and contracting stuff to get a smaller graph. Okay, so I hope this definition is clear. And we also can say that the graph class is minor closed if taking a minor doesn't leave you from graph class. So this is maybe a important way of thinking. We'll be talking about graph classes. I guess Michał in the first lecture, which was sort of a warm-up lecture, didn't really touch like this concept of graph classes. So graph class is just a family of graphs. Okay, I don't know, all forests is a graph class, or all salt trees is a graph class. I mean, it's just a set of graphs, and closed, I mean, formally you can say set of graphs closed undertaking isomorphism, but I mean, there's an utility definition, just some set of graphs somewhat defined. And we say that this graph set of graphs is minor closed if taking a minor doesn't lead to out of the graph class. So if you take a minor, you're still a member of a graph class. And maybe that's very abstract, but there's an important example of planar graphs. If you look at a planar graph, so a planar graph that's drawn on a plane, we'll be looking at a lot of about planar graphs later in the lecture. But if you look at planar graphs, then deleting a vertex or an edge keeps the drawing planar. I mean, you can still draw it on a plane, but also the observation is that contracting an edge doesn't break planarity. Yeah? If I contract, say, this edge, then I can still draw it on the plane. It will look like this, I believe. It will look like this, but I mean, I can still draw it on a plane, and this is like easy to see that if I contract an edge drawn on a plane, I can move these two vertices together to one spot, and I can still keep the embedding there. Okay, so if you have planar graphs and you know a bit more, you can, I mean, if you know that, I mean, you can generalize planar graphs to graphs embedded on a fixed surface, so I know a torus on a projective plane or whatever, or a torus with a few extra handles, then also like contracting an edges on such a surface also like keeps the drawing. You can maintain the drawing while contracting. So also like graphs embedded on a fixed surface is a minor closed graph class. I mean, taking a minor doesn't lead to out of the graph class, and this will be a very important example later in a few lectures. That this like, in some sense, will show that this is like the canonical, in some vague sense, the canonical example of a graph class closed undertaking minors, graphs embedded on a fixed surface. Okay, and what we'll be discussing today are graphs of bounded treewidth and graphs of treewidth, like treewidth at most 100. Treewidth is some measure that we'll introduce in like the next half an hour, but the graphs of fixed bound on the treewidth, which is some measure of the graph, will also form a minor closed graph class, and we won't discuss it exactly during this during the lecture today, but that will postpone to one of the tutorials either today or the week after. Okay, so that's like a definition of graph minors. And this is like a highlight of why we're really speaking about. So there is a theorem. I mean, this is actually Wagner's theorem, what I stated here. So Krotowski theorem is a bit slightly different about topological minors, but let's put it in one vague box here. So the point is that when they are not planar. So now let's take a step back and think in a very abstract, like categorical sense. Yeah, you think about, so we have got some graph class closed undertaking minors. Yeah, so whenever you take a minor, you're still in the graph class. So when you have got a set of graphs or a set of objects and some operation like some partial order, like contract, like up there, and you know that you're closed undertaking smaller things in this partial order. So you're downwards closed in this partial order. Yeah, you're allowed to take smaller and smaller graphs in this partial order of being minor here. Then you can define your graph class by minimal elements that are not in your graph class. Yeah. So you have got some graph class G that's closed undertaking minors. Okay. And you can think of the guys that are not in the graph class. So you can define like forbidden graphs of G, which are minor minimal graphs that are not in G. Yeah. So what does minor minimal? These are the graphs that are not in your graph class, but whatever operation you make, like minor operation, delete a vertex, delete an edge, or contract an edge, you jump into the back class. So that's minimal guys. Okay. And now you can make an short observation that like a graph edge is in the graph class if and only if for every f in this forbidden, f is not a minor of the graph H. Okay, so what I'm saying is that if I want to, if I have got some minor closed graph class, okay, and I have got somebody listed me the minimal guys that are not in this graph class, the minor minimal guys that are not in the graph class. If I have a new graph and I want to check if this graph is in this graph class, I may as well check if any of these minimal guys is a minor of this of graph H. Okay, so I mean to check. So if the guy is not in the graph class, then I should be able to contract it and delete. I mean, make a minor so that I make one of the minimal guys that are not in the graph class, minor minimal guys that are in the graph class. Okay, and so it's sometimes interesting. You have got some particular graph of minor closed graph class, and the question is like how complicated this graph set forbidden is. I mean, what makes you what makes you not in the graph class? So if you look at the example of planar graphs, so if you look at the example of planar graphs, okay, then you can, the question now becomes, what are the minor minimal guys that are not planar? So the graphs that are not planar, but whenever you delete an edge or you contract an edge or delete a vertex, you start to be planar. Okay, and there are two examples that are the canonical examples. It's like the K51, 5 vertex clique. Okay, this is the graph that's not planar, but whatever you delete here or contract, it becomes planar. It's like almost planar, but there's like one, I mean, you start drawing it and there's like one crossing and up there. And also K33. So bipartite graph with three guys on one side. This is the standard I mean, this is a standard example about like three houses and like electricity, gas, and water. You want to connect it, you cannot do it on a plane. Yeah. There, and there's like almost you can do it, but I mean, on the last moment you need to cross it. So these two guys are like minor minimal. I mean, whatever minor you take, they're planar for planar graphs, but they're not planar. And the Wagner's theorem really says that these are the only two minor minimal graphs for planar graphs, the only two non-planar minor minimal guys. Okay, and Kratowski theorem says this one's about the notion of topological minor, which we don't touch today, so I don't want to. Okay, so yes, so this is like segment. So it turns out that okay, we have got this abstract notion of forbidden guys, and it turns out that for planar graphs, the answer which guys are not planar but are minor minimal, not planar, it turns out to be actually very neat. And it's not that neat for larger surfaces, but still you can prove the fact that they are somewhat small. There are like finite number of them. Yeah, because on a high level, if you ask how nice the set forbidden is, you can ask the question, okay, well, is it finite or not? There's no reason to believe that even for some graph classes, like guys embedded on a torus of 5 handles, with 5 handles, whether like, can't you make like infinite amount of minor minimal guys up there. Okay, and this was actually Wagner's conjecture at some moment, that he thinks that if you look at minor relation, which is actually quite strong relation, I mean, you can do a lot of from one graph to another to get a minor, that actually the set form of G is always finite, that the set is always finite. This is a highly non-trivial statement. Okay, I mean, this is like a highly non-trivial conjecture and statement, because, for example, if you take the notion of being a subgraph or being an induced subgraph, there's graphs with like infinite, there are graph classes that are closed undertaking subgraphs, but the minimal guys, subgraph minimal guys that are not in the graph class is infinite. But here the conjecture that was open for a long while was that actually this one is always finite for the minor relation, and this was actually proven, and this is like the reason why we're talking this, and we're spending like 4 lectures around it. There's actually a long proof by Robertson Seymour that actually this is true, but it spans over like a few hundred pages and like 23 papers, and actually develops a new theory, like graph minors theory. Like a lot of theories developed towards proving this theorem. And this theory really involves proving that in some sense, the graphs of bound, like embedded on a fixed surface, is sort of a canonical example of minor closed graph class, that any minor closed graph class in some sense looks like a highly perturbed like graph class of guys of bounded genus, of like embedded on a fixed surface. Okay, and our goal for the next few lectures is to see some highlights, maybe not of exactly these proofs, but the tools used there, and like the theory developed around this proof. We'll have a very quick highlight of the proof later once we develop all the tools. But yeah, one of the main tools, and one of the tools that found actually a lot of applications in different places, is treewidth. Okay, and treewidth is the thing that we're going to study today and on the next lecture, and actually some things later, because I mean this will span a bit, and this turns out to be very important in many branches of both computer science and graph theory. Okay, so let's go for treewidth. So we go for treewidth. That was, so we finished the overview, or like the I don't know, the more like highlight or what we are going to do, and now we go to make some definitions. Okay, so treewidth is a measure, so we want to measure graphs. We want to make some width measure of the graphs that says how much this guy is tree-like or looks like a tree-like. And if you like about trees, you can also ask a simple question: how does this graph looks like a path? Yeah, so paths are very simple. Usually about paths, you can prove everything you want. I mean, decide if something is true very easily. And but you want to generalize it. So we want to say that this graph really looks like a path. And if you look at the graph below, this is really, I believe, like a second power of a path or third power of a path. Then if you look at the graph at the bottom, then in some sense, this graph is a path-like graph. I mean, if you can prove, I mean, some types of proofs of some types of algorithms, we don't touch much algorithms, but some types of algorithms that work on the paths may actually work reasonable of this type of graphs that look more or less like that. So you want to somehow define what does it mean to look like that, okay? To look like that. And also, if you look about trees, I mean, this is a tree, and this guy on the right also looks like a tree. Okay, this guy looks like a tree, and yeah. So, and you want to say that okay, some things work for trees, and they will work for trees, for tree-like things similarly as for trees. Maybe slightly more complicated, but it will still work there. Okay, uh, the way how you think about being tree-like is, I mean, this is a tree. I mean, on the previous slide, you have a tree, okay? But this is also a tree, like a star is also a tree. So such a guy should also look like, should also be tree-like. So, I mean, this guy is not that obviously like looks like a tree-like, yeah? It's just like a fixed star, but okay, we should treat it as a tree-like. So the main insight, if we want to try to define what does it mean to look at a tree, is to actually, or look like a path, is to actually think in terms of separators. This is like the most important, like the the plot twist, I would say now, that we are going to look at separators in the graph. What does it mean to be a separator? We're looking at vertex separators. So a separator, you have got a graph, so we can get a separator, and there is some set A and set B, and we can say that X is an AB separator if, I mean, when X, A, B are subset of V of G, okay, it says A of B, if there's no path from A to B that doesn't, every path, for every path from A to B, P visits a vertex of X, yeah? So you can actually think of this definition that something is a separator, separates two sets of vertices if any path from one set to another needs to visit somebody from X. Okay, so this is like a separator. In our sense, also, yeah, so this is it. And if you look about this path-like graphs, the thing that the way of thinking what does it mean to be a path-like is that there's like a sequence of separators sweeping the graph. So the intuition is like, hey, you can actually sweep the graph. You can actually sweep the graph using small size separators. And sweep means this was on this picture. Yeah, you go over, and in some sense you go over there and you sweep the graph using the small separators. Okay, and maybe a small highlight why this is useful is that let's look at this graph, and this is like also a path-like graph. Yeah, it's a subgraph of the previous one. So it should be like path-like as before. Okay, it's really path-like because it's a subgraph of a path-like graph before. And now there's this separator here that separates the gray area from the black area here. Okay, and the red vertices is some independent set. So say we are studying independent sets, or we are solving the maximum independent set problem, or whatever. I mean, any of this, I mean, do something with independent sets, some proof or algorithm with independent sets. And there's this small separator here. And the point of view is that we have got highlighted three independent sets in the left side. Okay. And the three independent sets have got the same intersection with the separator. They use the same vertex, the middle vertex from the separator. And the why separators are useful, for example, for maximum independence set, is that hey, the right-hand side really doesn't care which of these three independences on the right is really there. I mean, if you try to like reason or find some independences here, I don't know, take this guy and this guy. I mean, it's important for you that the middle guy from the separator is taken and the other two are not taken to the import. You're looking at the dependencies that take the middle guy from the independent set, and you really don't care which guys here are taken. Okay, so separators, I mean, this is like for independent set, but separators are very small separators are very useful to reason or compute something about many different problems, because sometimes the behavior of your object you're studying, or your problem you're studying, or property you're studying, can be actually on a small separator can only happen in a bounded number of time, bounded number of ways, or like limited number of ways, and you don't care what happens on the other side of the separator. This is an example of independent set. Okay, this is like a highlight or a vague way of saying why separators are important, or why sweeping by separators may make graph easier, or make how to use them in the proofs. Okay, good. So let's go to the definition. So we have got this definition of like sweeping with a separator, and let me propose the following definition. Okay, the definition is as follows. I want to say that the graph has path with at most some constant called PW here, if I can draw every vertex as an interval on a line. So I draw for every vertex an interval of a line. So f of vertex is the interval on the line, such that if there's an edge between two vertices, the interval overlaps. Okay, and the measure of the width of this decomposition, the measure of like quality of this decomposition, is how many guys overlap at one place. Sorry, I didn't want to press it. Okay, how many guys overlap on at one place? Yes, so here in this picture, at this place, 3 guys overlap, and that means that I say path with 2. So I subtract 1 really from this number of guys that overlap in one place. And how does this correspond to this intuition from the previous slide about like sweeping the graph? So you think of this blue line as the sweep line, yeah? So you have this blue line, and you're progressing from right to left, and you're sweeping the graph, yeah? You're going from right to left, and at every step, whatever this line intersects, is a separator between the guys that intervals that already ended on the left, and the intervals that are on the right. Yeah, because if the intervals are disjoint, they cannot have an edge between them. That's the first property. If there's an edge, then the intervals needs to overlap. So if the intervals are disjoint, there's no edge between these two vertices. Okay, so the guys that a, a vertical line intersect, these are the guys that separate the intervals, the vertices corresponding to intervals on the left, with the guys that have got intervals on the right. Okay, so now going in this model, in this interval model, going from left to right is like by this sweep line, this vertical sweep line is actually like sweeping the graph with small separators. And the size of the separator is path width. And why do we subtract this one? Just to say that the path has path width 1, because that sounds neat. Yeah, if you have got the path, say, I don't know, a 5 vertex path, this is a 5 vertex path, then the model will look like that. Okay, and there's always 2 guys at some time. I mean, if you have an edge, I mean, there's always 2 guys, at most 2 guys on one sweep line, and you need to have 2 guys on a sweep line to have any edge in the graph. Yeah, so paths will have got like maximum like sweep line size 2. And if you want to be neat and say that path width of a path is 1, because that sounds very neat, then you need to subtract 1, and that's why we subtract this 1, and this 1 will sometimes annoy us in many proofs. Okay, but now it looks neat. Okay, so this is path width. So once we got path width, so once path width, so okay, so maybe intervals, which are like intervals on real line, they may be sometimes nasty in the sense that it doesn't really matter, for example, if this guy ends a bit later or a bit shorter. Like there's a lot of freedom that we don't really need. And sometimes it's easier to look at it in a more discrete way. And the discrete way of looking at it is path decomposition. So this is really like a snapshots of this blue line, of the sweep line, snapshots when something important happens, like some vertex joins or some vertex disappears up there. And you can define it as like a sequence of snapshots. So a snapshot is like which vertices are currently intersected by the sweep line. So this is a path decomposition, like a sequence of subsets of vertices. They're usually called bugs. So so like the guys intersected by a sweep line at any moment. Okay. And yeah, so this is like another example. This is a bit more complicated graph on the left, and this is like a decomposition of the right. These are like these are just 4 snapshots. Sometimes you don't need really to snapshot every single event. In a sense, you need to only keep the maximal the maximal sets that the vertical line intersects. Okay, and now you want to encode this property that whenever there's an edge in the graph, two intervals overlap. That means that whenever there's an interval, these two guys need to appear together in one snapshot. They need to appear together in one bag, and every guy gets an interval which is not immediately visible in this snapshot. So you say that, I mean, a guy appears in a consecutive subsequence of consecutive interval of snapshots. Okay, so this is really now departing from the interval model from the previous slide. We can say that the path decomposition of a graph is like a sequence of subset of vertices that we call bags, and such that every edge is contained somewhere. So these two vertices meet in some bag, and every vertex appears in a consecutive segment of bags. Yeah. So the first one corresponds that the intervals of an edge overlap, and the second one corresponds to the fact that actually every guy gets an interval. Okay. And I hope it's quite visible that this is really the same as the previous one. If we just say that if we just now say that the width of the decomposition is maximum snapshot size, maximum bag size -1, and the path width is like the path width of the graph now is the best, because now we can minimize, like we can find it, you can look for the best path decomposition, the minimum width path decomposition of the path width of the graph is the best width of the decomposition we can find. Okay, so these are paths decompositions. So now now we defined something that how does it look like a path, and if now we want to replace path with a tree, we should just replace path with a tree in the definition. Yeah. So now we can say, oh, sorry, I forgot that I want to say one more thing. You can also think about, sorry for the mess up. I forgot that I wanted to say also here that you can also think of taking the snapshots every time something changes, and like distinguish, I mean, and saying one something changes, that's one interval ends or one interval starts. Okay, and this is sometimes called in the literature the nice path decomposition, that you start from the sweep line intersect on to the left, so that there's nothing there, and then it goes and has only one event at a time, like some interval starts or some interval ends, and this corresponds, interval starts corresponds that a new vertex joins the bag, or a new some vertex disappears from the bag if you go from left to right. Okay, so you can actually think of this, and sometimes some proofs or algorithms become easier if you look at the nice path decompositions, or if you look just at path decomposition. I mean, sometimes make useful to look at the path decomposition that is like very fine grained, that actually has one event at a time, and it's like very easy to take any path decomposition and turn it into a nice one by just like smearing out like the differences between two consecutive bags into first disappearing vertices and then appearing vertices up there. Okay, I hope this is visible up there. Yep, so this is sometimes useful. Okay, so going back to tree decomposition instead of path decomposition, let's try to just replace in the previous decomposition, so from the previous slide, just replace path with tree. What does tree mean? Yep, what would it mean? It means that now instead of path, I have got tree. So I got the tree. So this is the graph, and then I have a tree here. And every vertex, every node of this tree, let's call it, it's usually called a node. When at every node you have a bag, a subset of vertices, okay? And now, what does it mean? Okay, if if there's an edge, the guys need to meet somewhere. This is like the same statement we had before. And now if the vertex, the place where the vertex appears needs to be connected. This is like we previously said, it's an interval, and now in a tree interval it's not properly defined, so let's make it connected. Yeah? They're together, all these operations together. Okay, so this is the definition we made here, and this is actually the definition that will work. Like this is the analog of the path decomposition. Okay, this is the analog of path decomposition. This is the definition that will work. But what we want to say here, okay, apart from like adding, like let's going over, okay, H appears here in this decomposition, A appears here in this decomposition, and we can say, okay, the width of the decomposition is maximum bag size again -1, because we want trees to have tree with one. We'll see that in a moment, and the tree width is like the best possible width of a decomposition of the graph. Okay, so this is yeah, so this is the decomposition. Let's play with it to see if it satisfies our intuitions about being tree-like. So let's go over bigger example that looks a bit more tree-like than the previous one. So this is, let's look at this example and let's look at this decomposition. It's somehow like a bit didn't fit on the slide, but it's okay. So we have got this decomposition up there. And as you see, there's like the largest bug is of size 4 here. So the width of this decomposition is 3. We have this decomposition is 3. Here, there's a bug size 3, and maybe this another bug, and this another bug. And if you think about it, this what I'm just showing now, it looks like this intuition of sweeping a graph with a sweeping a graph with separators. Yeah, these guys that I show here are really like sort of separate the things in the tree. So that looks reasonable here. Okay. Okay, so let's go over the properties. You can think of the properties that, I mean, sometimes in literature, you add the property that every vertex is in some bag of the tree decomposition. This is really a very bogus like corner case that, I mean, if the vertex is just incident to an edge, already the statement that every edge needs to be in some bag already covers it. So you need to take care about isolated vertices, but isolated vertices can be added anywhere or just made it a separate bag for isolated vertex. So this is really like a not important property really here. But every edge is some bag. This is the important property. So for example, this edge is in this bag up there, and the bags that contain a single vertex are connected in the tree. Yeah, this is like, for example, vertex S is in this 4 bags up there in the composition. Okay, good. And the width of the composition was the maximum bag size by 1. And now I want to say the following property. Okay, now let's look at the separators. And the separators, I want to say the following thing. Let's look at an edge of the tree decomposition. Okay, so let's take as example this 2 bags here, this bag here, and this bag here. And let's look at the intersection of these 2 bags. Okay, this is like it's sometimes called the adhesion of this edge, adhesion of this. So the intersection of these 2 guys is actually these 2 vertices here, which are like dark here up there. Okay, and now this edge of this tree decomposition splits this tree decomposition into 2 parts, into the red part and the blue part. Okay, there's the red part and the blue part, and there are vertices that appear in the red part, and there are vertices that appear in the blue part, and the violet guys are the guys that appear both on the left and on the right. Okay, these guys in the intersection up there. And the point is that if there's a guy that say B here that appears only on the left, and there's another guy, say R, that appears only on the right, these guys cannot have an edge between them. Oh, R is also here. Cannot have an edge between them, yeah, because this guy appears only on the left, not in the intersection. So this B appears only in the red bags. R appears only in the blue bags. So there's no bag that it contains both R and B. Okay, just because one appears on the red and one appears in the blue. So they cannot be an edge between B and R. They cannot be an edge between B and R. Okay, that means that the intersection here, so the vertices that appear both in red and both in blue, yeah, so the intersection of these bags, so in this intersection, let me change the color. So this intersection, these are exactly the vertices that appear both in red and blue. Yeah, because every guy appears in a connected set of bags, like the guys that are connected in 3D composition. So whenever somebody appears, like G appears here and G appears here, okay, then if it appears in red and blue, it needs to appear on both endpoints of this edge because it needs to appear on a connected set of part of the composition. Okay, so the guys that the intersection of these 2 bags is exactly the set of guys that appear both in red guys and in blue bags. And the guy that appears only in red cannot see a guy that appears only in blue. Okay, cannot have an edge to the guy that appears only in blue, which means that the intersection is really a separator between red and blue vertices. So between the vertices that appear in the red bags and between the vertices that appear in the blue bags, the guys that appear both in red and blue, and this is the intersection of these 2 bags, is a separator. And because this is an intersection of 2 bags, this is small, at most treewidth plus 1, and we have got the separators. This is the intuition about sweeping the graph with separators. At every edge of the tree decomposition corresponds to the separation between the vertices appearing in one part of the tree decomposition and the second part of the tree decomposition here. Okay, And this is like the important property of the tree decompositions. And this is like why this definition really works and why this corresponds to the intuition of sweeping the graph with small separators. But now this sweeping is a tree-like in a tree-like fashion. So we discuss this sweeping intuition later in this thing. But for now, let's keep with these separations here. Okay, good. Okay, you can again, this is like a digression here, really. You can again make the tree decomposition slightly less intuitive than for the path decomposition, because for the path decomposition, you have this sweep line and you think of one event at a time. Here, you can also think of like going bottom up in the tree decomposition and having one event at a time, like a new vertex appears or a vertex disappears or something joins. There's like two children of a thing, but then first you can like change the bug so that these bugs are equal when they merge. I mean, this is like something that's mostly used for algorithmically, so I don't want to spend too much time here, but I want just to highlight something that there's something called nice tree decomposition, and you can sometimes in some proofs it makes sense to look at tree decompositions that like do one step at a time. Like you either have one child in tree decomposition, you're rooted, you either have one child that you introduce a new vertex, or you forget a vertex, or you merge something, but when you merge something, you have got the same guys in the back. So it's an easy exercise to turn any tree decomposition into a nice one without changing the maximum back size or the width of the composition. Okay, so that's I wanted just to highlight that these examples. This is an example of like this nice decompositions become a bit more elaborate than the standard ones. Sometimes it's harder to draw them, but you can think of like this graph of like okay, you on one side you take this PEF thing you and you add okay you start sorry you either do the BED, this triangle here, okay, then you forget D and you introduce go to BF, and also on the other side you can introduce BCF, forget C and introduce BEF. This happens here, and also now there's little visible, but also here you can first introduce EFH, forget H and introduce BF, and then merge all this BF from three sides into one branch and forget all these guys up there. Okay, so this may be maybe a bit too much here, but this is like a good example how does this nice tree decompositions really look like. Like introduce things, forget, and like whenever they want to merge something, they homogenize the interface there. Okay. Yeah, and the tree decomposition becomes a bit larger, but not much larger. I mean, the width is the same, but like number of bugs blows up a bit, but not much. Okay, good. Okay, so let's make back a digression with paths. We had because I want to sell you all possible points of view on the tree decomposition, or like most interesting point of view of the tree decomposition. So that's why so that you can use your favorite one or the most appropriate one in some proofs or whatever. So if you look at the, recall that path for path width, we had this intervals, yeah? Instead of path decomposition, we start with intervals. So every vertex is an interval line, and the guys that have an edge need to overlap, and like the measure of quality was how many guys at the same time are on one vertical intersect by one vertical line. Okay, and you can also think like we can engineer back the tree decompositions back to this intersection models. Yeah, so you can actually have that for tree. If you can look at it, you can have okay sort of a different way of looking at tree decompositions, having an actual tree like a topological object with like lines up there, and every vertex is mapped to a subtree. So on this picture, this is a very simple picture. So on this picture, for example, this vertex will become a small interval here. This vertex may become like, I don't know, something like that. This vertex will become something like that, say. This vertex will become a small interval here. I don't know. This vertex will again become, I don't know, something like that up to the endpoint. And this vertex may become just a dot here or a small subtree here. Okay, so you can think of the tree decompositions as an intersection model, like it's some sort of intersection model of subtrees of a larger tree. So the tree decomposition becomes a tree, and now every vertex becomes a subtree connected, and an edge means that the subtrees need to overlap, and your quality is like how many guys overlap at one place. overlap at one place. Okay, so this is another way of thinking. It's sometimes useful, so it's good to keep it in mind, but it's slightly because the tree changes between the graphs. I mean, for some graphs, you need bigger and bigger trees. You can, for example, always use a full binary tree, but it can be bigger and bigger depending on your tree, on your graph. This maybe it's not just a line, so it's not that often useful to think about instead of just 3D composition up there. And this is actually, if you look at it, this is like very similar to 3D composition. It's a bit more continuous, but sometimes for some people it's more useful to think about this type of intersection models up there. So I want to like look at it, just show you it. Okay. So there's another way of thinking, which is actually, so now I want to go back to this intuition that I want to go back to the intuition that this is sweeping a graph with small separators. Okay, so let me introduce a game. So if I want to make a sweeping, I want to introduce a game. So the game works as follows. There are K cops that want to catch a robber. Okay, so one player, there are two players. One player controls the cops, the other player controls the robber, and at every step the cops sit on some vertices, so they're like control, like they guard some vertices, and robber is in some other vertex somewhere in the graph. Okay, and I mean there are K cops, so the cops can occupy K vertices, and the robber, there's one robber, so he's at a single vertex at a time. Okay, and whenever if a cop ends up on a vertex together with a robber, then he catches the robber and cops win. That's the moment. And the robber wins if he can escape cops for infinite amount of time, like infinitely escape. Yes. Okay. So to start the game, just first cops say when there is, and then the robber says where he actually is there. Yeah, because the other way doesn't make sense. Yeah, so first cops sits on some vertices, so they say, okay, I'm sitting on those vertices, and then the robber, okay, if you sit here, then I'm starting in this vertex. And then how does the round look like? In one round, first the cops move. So what does it mean that the cops move? Think that every cop has a helicopter. So a cop can say, I'm staying here, I'm staying and guarding this vertex, or a cop can say, I'm flying to another vertex. Okay, so this really means that the cops say which is the next set of vertices occupied by cops, and then the intersection, like the intersection of the previous vertices and the new vertices, these guys stay, and the guys from like C minus C prime fly to C prime minus C up there, so fly to the new vertices. Okay, but while they fly, so the guys that stay, they guard their vertices. But while they fly, the robber can move. So the robber doesn't have a helicopter. The robber has a very high-speed motorbike, and the robber just travels along the edges of the graph to any other vertex. But he cannot cross a vertex that's occupied by a cop that decided to stay in the guard. Okay, so the guys stay. The cops that stay, they guard the vertices to make these vertices not passable by the robber, and but the robber can move anywhere there, and then the cops land where they're where they start the decided area to go. Okay, so let me emphasize here that this is like a full information game in the sense that the robber knows where the cops are flying to, and the cops know where the robber is, but the cops announce the set C prime before the robber announced the set C prime before like they know how to rob it. So the cops announce the set C prime, the guys from C minus C prime take off, and then the robber decides where he goes. And then the guys land, they cannot change their fly path in the meantime. They land when they where they start to fly. Okay, so this is like the game how it works. And now, what I'm going to argue in a moment, by going back to the decomposition a bit about, is that if you take the back size of a tree decomposition, I want to convince you that a tree decomposition is a strategy for cops. That if you have got a tree decomposition with k maximum back size k, then k cops can catch a robber, and the tree decomposition is actually a strategy to catch a robber. And the cop's strategy to catch a robber is really like a sweeping thing. So you want to think of this C intersection C prime as like this adhesion where the guys separate the blue part of the graph from the red part of the graph and don't allow the robber to cross from the blue part to the red. Okay, and the tree decomposition is sort of like a strategy how to corner the robber in one side of the graph. Okay, So let's go back to our example and let's try. I hope the definition of the game is clear. Let's go back. Oh, let's go back to this picture, and I think I want to go back here. Okay. So what I want to say here, so I want to say that, okay, here maximum back size is 4. So I want to argue that I want to show an example, and this will be like a example, proof by example, that actually robber cops can actually catch. So I have got 4 cops, and I have got 4 cops, and I want to catch the robber in this graph. Okay, so say at the beginning, so the strategy is to have the guys always on one back of a tree decomposition. So I have got this tree decomposition. This is my strategy for cops, and I want to always keep the cops on one back of the tree decomposition. So say I start with this guy, with this thing. So my cops initially land on this 4 vertices. So this is round 1. Okay, they land here, and now the cop says where he is. It really doesn't matter where exactly he is. He really says whether he's in this connected component, or disconnected component. So say that he's on vertex P. Okay. So say that the guy is on vertex P. So it actually means that he's in disconnected component, yeah, because he can move arbitrarily between them. Okay. And now what I'm doing here, so how does the cops look? So the guy, where is the guy? This is the bag, and the robber is in one of this. The robber is on vertex P. So vertex P is here. P, oh, it's actually only here. Okay, it's actually only here. That means that I want to move my cops into the direction of this component. Yeah, in this direction I want to move this cop because P lives here. So what I really want, this is my C, and I want this one to be my C prime. I want to move my caps into, like, by one back into the direction where where are the backs where the robber is. Okay. So what I want, I define C prime to be GIS, and C was GHIF. What does it mean? That means that the cops at G and I, they stay and they guard. Yeah, this was this was the separator. Yeah, this was the separator. If you look at this thing, this was the separator between the red part and the blue part. That the guys in G and I guard such that the robber cannot go to the red part. The robber cannot go to the red part. Okay, while my guys from F and H, from these 2 vertices, they fly to S. I mean, whatever. One of them is just slacking off, but one flies to F. Okay. So now my guys, now in the second round, I'm occupying these 3 vertices. Okay. But meanwhile, the guy moves. And the guy moves either moves to one of these vertices here, okay, or he moves to W. Yeah, he can also decide to move to W before the guy on S lands. He can move to W. Okay, and now if say the guy says, okay, I'm staying at P, then in my next step, okay, if the guy says I'm staying at P, then in the next round, okay, but the guys now are G and S. So in the next steps, I will define like C double prime, like the next step, to be G, Q, and S. I will move to the next set of, to the next back in the tree decomposition, okay? So what does it really mean? That means that the guys at G and S, so guys at, let me just change the color for now. The guys at G, the pink guys, the G and S will stay, and then we guard again so that the robber cannot cross the separator, and the new guy will land on Q. Okay, and in this manner, I will always have the guys that stay on adhesion, so they stay on a separator and doesn't allow the robber to go from a box in one part of the 3D composition to the box in another 3D composition, and the guys flying will occupy the next bag in a small, making the part of the 3D composition where there are vertices with robber smaller and smaller. Okay. And yeah, and because I know where the robber is as a cop player, I can always like go into the direction of the cop. So let's rewind this. So say that actually in alternative world, the robber decided to go to vertex W up there when I'm set that C prime. When I said that I'm landing on G, I, and S, he decided before I land on S to go by his motorbike to W. Then then in the cop rounds too, the cops will be here, but the robber say green, is in W. So now I want to go in this direction in the tree decomposition. Yeah, I'm going always into the direction of this component of the tree decomposition that contains the vertices of with rubber. So now I would define C double prime to be actually ISW, which means that the guys on I and S, so here and here, will stay and they will guard so that the robber won't escape, and the guy on W will land on the robber and catch him. Okay, so I hope that I convinced you by this argument that, I mean, this is not super forward proof, but I hope I convinced you that if I have got a tree decomposition with maximum back size k, then actually this tree decomposition is a strategy for cups to cop for k cups to catch the robber. Actually, this tree decomposition is a strategy for cops. Okay, so this is it for that one, and this is like the intuition about sweeping. And what will be, so let's go back to the definition. So what will be on the next lecture, and this will be like the main topic of the next lecture, is that robber can escape through one less cops infinitely, can infinitely. Okay, for infinity. What does it mean? That means that this is actually this cops and robbers games is actually a good characterization of is actually a very good characterization of the of treewidth. That actually like the minimum number of cops needed to catch a robber is exactly treewidth plus one, which is like the maximum back size, which is should be the correct treewidth, but it's not. Yeah. So yeah. So but if you think about it, it was quite simple to see that the tree decomposition is a strategy for cops. But now how to make strategy for robber? Yeah, we now want to say, hey, actually, if you cannot find a tree decomposition of smaller width, then actually robber can always escape. So what we'll be developing in the next lecture, we'll be developing a dual object for a tree decomposition. We'll be developing like a tight obstacle. It will be quite abstract. A tight obstacle, it will be called bramble. It will be like a tight obstacle. What's like an obstacle to make a tree decomposition of smaller width. Yeah. So we'll be having, okay, if you can find a tree decomposition of some width, that's fine. Fine. But if you cannot decrease the width, that there is a reason for that. And the reason is called the bramble, which will be a quite abstract object in the graph that will be actually, it can be viewed as a strategy for robber, to escape the cops. Okay. For an infinite amount of time. Okay, good. So, but that's like the highlight or like an advertisement for the next lecture, so that we will come for the next lecture. And now I want to do something slightly different, okay? Because brambles are quite abstract objects, and the problem with brambles is that they can be of exponential size. In a sense, that tree decomposition is small. You can argue that there's always linear in the size of the graph. Like it does make sense to make larger than linear in the size of the graph tree decompositions, while brambles are actually sometimes necessary to be exponential size, and that's one of the reasons why brambles are slightly not that super useful in many outcomes, but it's important because they're like the tight objects for tree. And for now, I want to discuss a few background things, and I want to discuss uh, computing treewidth, because computing treewidth gives us another very valuable insight to treewidth. Okay, so I want to first do a quick historic look at treewidth. So actually, it turns out that this notion of tree-like stuff, it was very useful in many contexts. So actually, in the 80s, there were a bunch of different definitions. There was a bunch of different definitions, like it was called partial K-trees, there was branch tree, and there were a few others. So in a few different concepts in logic and in some database theory and other places, graph theory and algorithms, people defined something which was treewidth or like mutated treewidth or something very similar to treewidth. The definition I showed you was the definition by Robertson Seymour from the graph minors series, and this is the one that turned out in the end to be like the established ones. But if you notice something like branch treewidth in the literature, this is something similar to treewidth. It's not treewidth exactly, but this is very similar notion to treewidth. And partial K-trees is more or less exactly treewidth. Okay, so these are the notions that are very similar. They essentially describe the same phenomenon, but sometimes there's like, I know, off by one. Branch width can be like 1.5 treewidth or something like that. So, but they describe more or less the same phenomenon in graph theory. Okay, so first thing, we have got like the algorithmic people use it a lot, and this is something that you can learn on the Algorithmica course, and you can also learn it on the we could have learned in the previous semester on the parameterized algorithms course that like graphs of bounded tree are very useful for algorithm design. For example, from the thing that I hand waved about independent set, you can actually deduce that finding maximum independent set in a graph is can be solved into the tree time times some polynomial in the graph size. We'll try up there, but that's like not the topic of this lecture. Uh, in the graph theory, as you say, this was as we are speaking about it because tree decomposition tree is one of the main tools used in the graph minors theory up there. But also the logic people like tree because it turns out that bounded tree graphs is exactly the maximal class of graphs that where monadic second order logic queries can be efficiently computed. Which means that this is the logic where you can quantify over subsets of vertices, subsets of edges and subsets of vertices. And the dynamic programming algorithm, I mean, this is like the correct logic formulation of like the class of problems you can solve using dynamic programming on graphs of bounded tree, which is again something we don't want to discuss here. But this is the reason why the logic people were in the 80s, starting from the 80s, interested in graphs of bounded tree, and why they defined their own way of defining it at some moment. Okay. Good. So this is like a highlight. And now I want to think about computing TrueIf. So I don't really want to compute TrueIf. I want to use it as an excuse to have some good insight into the structure of graphs of bounded TrueIf. But I mean, this is an important piece of knowledge, so let's go over it. So apart from using the 3D composition, we sometimes want to compute it. And it turns out that computing TrueIf optimally is an NP-hard problem, so you don't expect a very good. In particular, that also means that you don't expect an easy to describe obstacle for truth. Yeah, there shouldn't be like a CoNP certificate for high truth. Yeah, there shouldn't be like a counter easy to describe and verify proof that a graph has got higher truth than you think. Okay, so that's why brambles are complicated. Okay, and also like there are some reasons to believe that you don't get good approximation, but and the best known approximation like root log tree. So you can find like given a graph, you get a graph k and either k. You can either say tree if is larger than k, or you find the decomposition of with order of k root log k. Okay, yeah, so it's an approximation algorithm out there like that. Okay, and the point is that okay, but this is like polynomial time, but since on the algorithmic side at least we're later doing exponential things in TrueIf, we can also do exponential things in TrueIf to start from to compute the bounded TrueIf, guys. And there's actually like 3 results in this direction. The pure result is that you can spend time roughly k to the k cube to decide whether TrueIf is at most k or larger than k. Okay, this is quite a complicated algorithm, and we don't want to go into details, and this is not the subject there. What we will do now, and what's our plan for the last half an hour, is to get some insight from this algorithm. So this is an algorithm that, given an integer k, it doesn't exactly say whether truth is at most k or larger than k, but it says, hey, the truth is larger than k, or maybe it's smaller, maybe it's larger, but there's a tree decomposition of with like order of k, like 4k. We'll get, I don't know if we get exactly these numbers in the proof in a moment, but but let's but I don't promise you exactly these numbers here, but there's really order of k in the proof I will show in a moment. But the problem here, what we'll get here will be like a quadratic dependency on the size of the graph, which is sometimes problem if you want some applications. So there's actually an algorithm. This piece, Michał, this piece, my brother. There's actually an algorithm that gives like slightly worse constant scares, but it gets like the best of two worlds. It gets linear dependency on n and constant to the k dependency on the tree up there. Okay, so there's actually like some you can get linear time and c to the k constant approximation for true. Okay, but that's not that's like side knowledge here. The important part is that now we are going to look at some variant of this algorithm. It's actually, if somebody wants to look at it, it's actually described in the parameterized algorithms book. If my description in a moment won't be that great, then this is like you can look also in this book. But yeah, and also I think Michał also described it on parameterized algorithms course. So For some of you, it may be actually visible. Okay, so let's try to make an approximation for going for treewidth. And this is our task for the next 20 minutes. And let's go here and let's do it. Sorry for this mess up. Okay, so what I want to say here is that let's compute let's compute. So let's think in the following terms. We want to have got some recursive algorithm that computes treewidth. Okay, so I have got the graph G, but I don't want. I mean, the recursive step will be like, okay, I have got some part of the graph G. Okay, so I have got some part of the graph G, so this is like some subset of V of G, but I also have got some set S here that's like the interface to the rest of the graph. So the other parts of the graph, they actually connect to the set S. Okay, and I want to keep these connections. Yeah, I want to use S as the separator between A and the rest of the graph. Okay, I want to use S as the separator between A and the rest of the graph. So what I really want there is that I want so what I want there is that I want the like this guy to be separator, and remember that separator, this was contained in one edge or one back of the graph. So what I want, so from the recursive decomposition, like if I want to invoke the function f for the set A and set S, what I want from it, I want the tree decomposition of G of A that I can attach later. I can use S as a separator. So I want to be S in a one back, such that S is contained in one back of this tree decomposition. Yeah. So what I want to get here is that I wanted to decompose this graph, but not only decompose this part of the graph, but I want to have got the S as like a separator to the rest of the graph. I want to S to be hidden in one back of the tree decomposition. Okay. And I want this tree decomposition to be small. Okay. And now okay, but I want this width of this tree composition to be really small. What does it mean? That means I want this one. Yeah, so I want. So I don't want this S to be set to be set too large, because if I give my recursive step a too large set to decompose, then to the too large set to put in one bag, then of course this bag that contains S will be large. So I want to keep the invariant that the set S is bounded, and I think the correct bound is something like 3k plus 3. I think this is the correct one. So I want to keep this invariant that the set S is of size at most 3k plus 3. Okay, and let's describe this algorithm. So there's like some base cases. In the base case, if A equals S, that means that there are only like S are the only vertices, then we just return the tree decomposition that contains only one back S. Okay, there's nothing to do. This is like a narrow tree decomposition. It's like the base case, and there's an easy case. There's an easy case where the set of S is smaller than our bound. Then we just add a new vertex to S. Then we just recurse on F of A and S union any vertex U for some U in A minus S. So we just expanded the S by a new vertex. Just, I mean, add an extra things. I mean, there's nothing interesting here. This is the easy case. Like what I'm going to say now is that the interesting case is when the set S, the separator to the rest of the graph, reaches some maximum bound that we want. Remember that we want to say that treewidth is larger than K or compute a tree constant of width, like at most, I know, 4k plus 4 or something like that. Yes, or small 4. So what we want to say is that, hey, if the important case is that, okay, our current separator that we want to keep to the rest of the graph reached 3k plus 3, and hey, what do we do with it? And this is an important observation. So assume that the graph has got treewidth at most k. So let's change the color. So this is a graph theoretical observation. Assume that the graph of G has got size most k, and let's look at the tree decomposition of optimal size. Okay, this is a tree decomposition. Okay, but there's this set S. Let's make this set S red. Okay, this set S red, and it appears in this tree decomposition somewhere. Okay, it appears in the tree decomposition somewhere, in some places. Okay, it appears, and note that because the set S now has got size exactly 3k plus 3, it's much larger than one bug. So one bug is of size at most k plus 1, okay, because treewidth is at most k, okay. So this set is spread along a lot of bugs, okay. So we, for every edge, let's take a orange color, and every edge orient into direction where there are more vertices. I mean, at every edge, we look whether there are more vertices of S appearing on the left and appearing on the right, and we orient the edge in the direction where there are more. So we orient every edge in the direction where there are more, and if there's an equal number on one side and the other side, just orient arbitrarily, just direct to, but orient to the more, okay? And this will be like a orientation like that of the graph, yeah? This will be like, if this edge is like that, then of course this edge needs to be like that. There are even more guys in this direction up there, okay? So this is really like an in-branching orientation. So there's like a guy of out of degree 0, yeah? So so I proved here is that there exists a bug X such that if I remove this bug from the graph, every connected component contain at most half red vertices of S. Okay, so what I want to say is that, okay, if I oriented this edge in this direction, that means that the guys appearing here on the left side of this tree decomposition, they're at most half of the red vertices of S. Okay, so what I proved here is that, well, I proved the statement that there exists a set X of size at most k plus 1, so that for every connected component C of G minus X, okay, is at most S half. Okay, what I proved here is that for every connected component C of G minus X, the number of vertices that of red vertices at most as half, because the edge was oriented towards this back up there. Yeah, this is the back of seismos of there. Okay, okay, but what does it mean? This, okay, what does, so this component up there? What I want to say here is that, hey, okay, but this is almost as half. Good. So now, if I have this X, now let's, okay, so let's go, I will go use this one, yeah? Sorry for that, I will use this one. So I have got this, recall that, oh, sorry. I have got this set A and I have got this set S that has got 3k plus 3 vertices, okay? And I know that there's this, exists a set X, which I don't know, will be green here, X, such that for every connected component, actually G of A, let's look at G of A, applying the previous lemma to G of A minus X, contains at most size of S half vertices of S. Okay, good. What does it mean? There's a simple argument to say that, okay, but these components, I mean, there can be many of them. But I want to find such X. Okay, I want to find such X. So what I want to say here is that, hey, actually, what does it mean? That means that I can, I mean, from this I can imply that the fact that there exists a set, call it Y and Z inside A. So there's, you think of Y being this and the Z being this, okay, such that there's no edge, such that Y union Z is everything, no edge from Y minus Z to Z minus Y. Yeah, so the intersection, think of X being the intersection between them, such that Y intersection S is smaller than 2/3 S, which is 2k plus 2, and Z intersection S is smaller than 2/3 S, which is 2k plus 2. Yeah. So what I said here is, okay, I have got, I mean, this is like a standard counting argument. If I have got a separator that after removal, every connected component contains at most half of the red vertices, they can group these components with red vertices into two groups, Y and Z, such that such that each of them contains at most 2/3 of the red things. Yeah, because the worst case is that when I hit, I got 3 components of 1/3 each. Then grouping into 2 components is really 2/3 and 1/3. Okay, so this is like standard grouping algorithm that we may have seen somewhere. So I've got this picture. And now what I want to say is that I can actually find such end separation because I can iterate over all options of y intersection s and z intersection s. So I can look at this set and this set. Okay, this is like 3 to the size of s options, which is in y, which is in z, and which is in both. Okay, and I can find like a minimum cut between them. Yeah, so what I mean, let me say what's going on there is that, hey, there's actually this set S, and if I look at y intersection z, okay, here there are at least k plus 1 vertices. Oh, and here intersection y intersection z is no k plus 1 because this is the separator. Yeah, this is at least k plus 1 vertices, and this is at least k plus 1 vertices. Okay, so both these sets are size at most k plus 1, but this set in the middle, this set is at most k plus 1. Okay, okay, so this is like there's a separation like that, and I can actually find them in reasonable time. I can find them in like 3 to the size of s time. Okay, and what I'm doing now is that now I recurse. I made a bag that contains s union y intersection z. Yeah, so this bag has got the size 4k plus 4. This bag has got the size 5 plus 4. So I make this guy, all these guys as one bag. This is the bag that contains s. And then I attach to it a recurse on f of y. And now I want to have got actually z on this side, z. And I want to have got this part. So I want to have got y intersection z and s intersection z. Yeah, so I want to have got on one, I want to recurse on the red area here. This is the red area with this boundary. And in the other way, I want to recurse on the pink area with this as the boundary. So I want to recurse on f of y and y intersection z plus y intersection s as the thing that needs to be stored in the boundary up there. Yeah. So the crucial observation here, I mean, the details of the recursion is not that important. The crucial details here is that actually, if you go back to the previous slide, the fact that once you get set of size like 3k plus 3 or larger, then there's actually a small separator, a small balanced separator that splits it into smaller, that splits it into sizes of size at most half, and has size k plus 1. Okay, have size k plus 1. Okay, yeah, so that's up there, and then we can use it algorithmically to like make the next step of the tree decomposition, add the separator to the back, and recurse on the connected components up there, or recurse on the two sides of the separator, and in this manner keep the set as quite small, because now this thing is small because you added k plus 1 guys here, but you removed k plus 1 guys here. Okay, so this set is still not larger than the previous set S in the recursive step. Okay, okay, sorry if that was too vague. The thing that I want to drag out of this algorithm is actually this observation about the set S, that when the set S grows too large, you can always shatter it into small pieces with small separator. Okay, so the observation that we had, and let's go to the very end then, sorry, here, the observation we had, read the observation we had, if the treewidth of G was at most K, then for every set S, there exists X, okay, of size at most K plus 1, such that, actually maybe let's look at the separation. Let's look at the separation thing, not X, but there exists YZ inside V of G. That were like, they were the size of the separation. So they together formed the entire graph, and there was no edge between y minus z and z minus y. Yeah, so there were like the composition of the graph like that, y, z, and there was no edge like that. Okay, and the size of y minus z, the middle part, was small, such that the size of y intersection s was at most 2/3 size of s, and the size of z intersection s was at most 2/3 size of s. Okay, so no, that I don't want to say. Yeah, I want to say there's this stupid, no, there's a stupid example of, it's not exactly what I want, because there's a stupid example of S being, for this particular statement of S being a single vertex thing. So I think I want to say that here, sorry, actually size of Y intersect minus Z intersection S and Z minus Y intersection S. Yeah, I think this is the thing I want to write here. Sorry. I mean, if I don't bound the size, if I don't give a lower bound the size of S, then I need to be aware of like S being like a single vertex stack. He's not splittable. Okay, so I want to say this statement. Okay, and now, so in a sense, whenever your set becomes too large, there's a way of splitting it. Yeah, whenever this, if there was a set which is like, I don't know, larger than 3k plus 3, then the separation into the y part and the z part actually has got this part being yeah, this part being at most 2k plus 3 and at most 3k plus 2k plus 3 here. Okay, so let's don't be picky about the numbers. If I put the set of being at least 300k here, or 300k plus 300, okay, then this part is at most 200k plus 200. This case 200k plus 200. Okay, which means that there's like some sort of balance split, and of course the middle part is most k plus 1. Okay, so there's some split up there. In particular, there's no way of pushing, like if I choose 2k guys here, and if I choose 2k guys here, 2k plus 2 guys here, and 2k plus 2 guys here, there's no way of making a flow, like a disjoint paths, 2k plus 2 disjoint paths from left to right, because there's this bottleneck in the middle of size k plus 1. Okay, so what I said, what this algorithm really relies on is that whenever you have got the set S and the set S becomes too large, there's always a way of splitting it in a balanced way, or actually splitting, there's always a way of splitting it such that this thing is smaller than this area and smaller than this area. Okay, so there's always like a way of splitting such that the thing how you split, the separator is smaller than the things completely on the left and smaller than the things completely on the right. Yeah, that's the way. And now, if you think about it, like a set S that you cannot split in this fashion is an obstacle to true width. Yeah, and this is the notion of well-linked set. This is the last thing I want to drag out of this proof and like prove it, is that the well-linked set is a set that, in a sense, you cannot split it. Like a set is well linked. Let's look at this definition here. A set is well linked if whenever you choose two disjoint sets of equal size inside, okay, you can always join them with disjoint paths. You can always join with disjoint paths. And notice that here, this is really proof that you cannot have a set of size 300k plus 300, a well-linked set of size 3k plus 300 graphs of 3 if at most k, because the separator will actually prevent you from having 2k plus 2 paths from set here to set here. Okay, so that's like an obstacle. So what we have proven here really is that the like if true if of G is at most k, then the maximum every well-linked set, every well-linked set is of size at most. Okay, here we prove 300k plus 300, but actually the bound is more like, I don't know, 3k or 4k or something like that, but I don't want to be picky about this. Yeah, so large true, so a small true if means like small true if means that you can't have two large sets, but also there's another way around. Yeah, if you don't have well-linked sets, I mean, if you don't have large well-linked sets, then this algorithm that I presented you will compute a tree decomposition of small width. That's like the important message, that if this algorithm, what it really says, it has got a subgraph of a subset of vertices and some interface he wants to keep in one bag, and he grows this interface, and then when it's large, it tries to separate it using the fact that this guy cannot be well linked. Okay, if this guy is not well linked, he separates it with a separator, proving that it's not a well linked, and in this manner it makes a progress. So what we really proved here is that if the maximum size of well linked set is, I don't know, L, okay, then the true if is smaller than something like, I don't know, 2L plus 2 or something like that. Yeah, that actually you can. Yeah, what we actually proved here is that if the maximum size of a well-linked set is something, then the algorithm will actually provide you a tree decomposition with like double the maximum size of a well-linked set. Okay. So what we have really proved here, what this algorithm really proves, is that the maximum size of a well-linked set in a graph is like off by a constant with the tree of the graph. Like this is like another type of obstacle, or another type of dual object to the tree. Like we will have Bramble in a week, but now we have got well-linked sets that, hey, I mean, okay, they're not tight, but small tree means that you cannot have large well-linked sets, and lack of large wedding sets made tree small because this Robertson similar approximation algorithm that I sketched a while ago, actually like the only moment when it actually says I cannot make any progress is that actually the S is well linked in G of A and he cannot find any separation there after. Okay. So this is like how it goes. Sorry for the last part being a bit messy. And I think this is the moment when I want to finish. I want to go to the last slide. This is the thing that, so I prepared the correct constants here. At least that having a weighting set of size 3k plus 2, 3 means that the tree is large, at least k. And no Welling sets means that the algorithm will produce something like 1.5 of the maximum size of a Welling set. This algorithm, I mean, I thought through the exact constants, and I think these are the ones here that you can get from the arguments I presented you, if you are careful, plus ones, all these things up there. Okay, I think that's done. Sorry for messing up the whiteboard, but yeah, that's what I wanted to present you. Thanks a lot. Do you hear me? Ah, okay, I'm stopping the recording.